All right, let's get straight to it. In this briefing, we're diving deep into the massive transformation happening right now in automotive electronics. We're going to cut through the noise and deliver a clear, actionable strategy for you, the engineering leaders who are actually building the future of EE architecture.
Okay, look at this. This one slide really tells the whole story. On the left, you've got the past. That's the distributed architecture. Honestly, it's a tangled mess of wires. It's heavy, it's incredibly complex, and it's a nightmare to update. Now look to the right. That's the future. A zonal architecture. Clean, logical, organized by physical zones in the car. This isn't just about cleaning up a wiring diagram, you know? This is a fundamental rewiring of the vehicle itself. It's the absolute key to unlocking the software-defined vehicle everyone's talking about.
So here's our game plan. We'll start big picture with the zonal revolution itself. Then we're going to drill down into the two most critical hardware challenges, the zonal control unit, or ZCU, and the telematics control unit, the TCU. From there, we'll look at the foundational tech that makes it all possible, and all of that leads us to our single most important strategic recommendation, what we're calling the co-design imperative.
First up, let's put some hard numbers on this shift, because to really get the urgency here, you have to see the data. We're not talking about some slow, incremental change. This is a massive, exponential transformation.
23.2%. Let that sink in. That is the projected compound annual growth rate for zonal control units. The market is just set to explode, hitting 172 million units by 2032. For any engineer in this space, a number like that signals one thing very, very clearly. Zonal isn't some far-off concept. It's the roadmap for right now.
And here's the money shot. By 2032, we're looking at a market of over $800 million for just the power management silicon inside these systems. What that tells you is that the real value isn't just in the number of boxes. It's in the incredibly sophisticated, high-value electronics that make them tick. All right, let's drill down into the first critical node, the zonal control unit, the ZCU. The best way to think about this is as a new regional hub for the vehicle's nervous system. It's gathering up all the local signals and distributing power right where it's needed.
So the ZCU is really where the physical car meets the digital brain. It's handling I/O, it's a power distribution hub, and it's a local processing unit, all rolled into one. But here's the problem. You're trying to cram a powerful 32-bit MCU, a complex power management IC, and all the passive components you need into a tiny sealed box. That creates an absolutely immense engineering challenge.
And this is where we get down to the nitty-gritty physics. The advanced chips that give these systems all their smarts, they run on less than a single volt. But they are thirsty. They demand these huge, instantaneous gulps of current. So the challenge is feeding this beast while keeping the voltage stable inside a razor-thin window of just 30 millivolts. You drift outside that, even for a microsecond, and the whole system can crash. Now this slide is perfect. It lays out the problem and the solution side by side. On the left, you see that voltage droop, that dip right when the processor demands power. That's the failure condition we're trying to avoid. And on the right, that's the elegant architectural fix, a distributed power system. You have a main PMIC and a smaller sub-PMIC. This lets you deliver power right next to the load, which is exactly how you stabilize that critical voltage. But here's the kicker. That brilliant PMI architecture, it can't work in a vacuum. It absolutely relies on a whole new generation of high-performance passive components. We're talking about special metal power inductors that handle huge currents without breaking a sweat, tiny miniaturized capacitors that you can squeeze onto a crowded board, and materials that can reliably operate at a blistering 150 degrees Celsius. The active silicon solution is completely dependent on these passive enablers. Okay, let's shift gears to the second critical node, the telematics control unit. So if the ZCU is the vehicle's nervous system, the TCU, well, it's the car's mouth and ears. It's the one and only digital gateway connecting the vehicle to the entire outside world.
The TCU is basically trying to conduct a symphony of radio frequencies. You've got 5G, you've got V2X for talking to other cars and infrastructure, and you've got GNSS for precise positioning. And it has to juggle all of that while feeding critical data to systems like ADAS. The real challenge is making sure this symphony plays perfectly, even in the most hostile environments you can imagine.
So let's just imagine a critical failure scenario. You have a level 3 autonomous car, it drives into a long tunnel or maybe into a dense city with tall buildings everywhere. Poof, the satellite signal is gone.
How does that car know exactly where it is, its precise speed, its heading? Without that data, your advanced safety systems are suddenly flying blind.
The solution is a technology called dead reckoning, and it's powered by a 6-axis inertial measurement unit, or IMU. This is a super sophisticated little sensor that's constantly measuring acceleration and rotation on all 3 axes. The moment the satellite signal disappears, the IMU takes over, calculating the vehicle's path with incredible accuracy. This isn't just a cool feature, it's a critical safety requirement that meets automotive safety standards all the way up to ASIL-D.
And how do you protect these incredibly sensitive communication modules from the brutal reality of automotive life? Constant heat and vibration? Well, the solution here is physical. It's a specialized resin mold packaging that literally seals the important components in. This helps dissipate heat and provides rock-solid mechanical stability. It's what keeps the car's gateway to the world open and reliable, even when the temperature hits 105 degrees Celsius.
Okay, so we've covered the ZCU and the TCU. But now we need to talk about the foundational technologies that hold this entire system together. Because without rock-solid power integrity and functional safety, none of those advanced features we just talked about can ever be trusted.
Every single high-speed data line and power converter in a car generates electromagnetic interference, basically electrical noise. That before line on the graph, that's the raw noise. It's enough to disrupt communications all across the vehicle. That after line shows what happens when you apply a smart multi-stage filtering strategy. Meeting that strict CISPR 25 Class 5 standard isn't a nice-to-have. It is absolutely non-negotiable for system reliability.
And this slide really nails a critical strategic point about functional safety. It is not the job of one single component. It's a system-level promise. On one side, you have active monitoring. That's the silicon's ability to constantly test itself and report any faults. On the other side, you have passive reliability, components that are just designed and certified to be so robust they simply don't fail. Real safety, true safety, is when you bring both of those philosophies together.
And that brings us to the core strategic recommendation of this entire analysis. The challenges we've just outlined in power, density, connectivity, and safety, they are all so deeply intertwined that you just can't solve them in separate silos anymore.
So here it is, the single most important takeaway. You cannot simply go pick the best PMIC out of one catalog and the best inductor out of another and just hope for an optimal result. It doesn't work that way anymore. The physics of delivering power at these densities demands a deeply integrated approach from the very beginning.
This diagram is the strategy. The optimal solution is found right there, in the overlap. It's a co-designed strategy. It's where the active silicon from a company like Renesas and the foundational passive components from a company like Murata are engineered, simulated, and validated together as a single system. This symbiotic relationship is how you solve the voltage troop. It's how you solve the thermal issues and the EMI challenges, not as individual problems, but as a complete system.
So let's just quickly summarize. 1. The move to a zonal architecture is happening. It's the only way forward. 2. This shift creates huge, extreme challenges in power, heat, and signal integrity. 3. You can't solve these problems with a piecemeal approach. It requires systemic co-design. And that means active silicon like PMICs and passive components have to be developed together. At the end of the day, this deep partnership is what will truly enable the software-defined vehicle.
So, we'll leave you with this one final thought. As you and your teams navigate this massive transition, the most critical question you can possibly ask is this: is our hardware strategy built on just selecting isolated components, or is it truly built on a foundation of systemic code design? The answer to that question will likely determine your success.